Howdy y'all, Mr. Avil here. Today we're going to go over the 4.7 notes, which is all about our inverse trig functions. All right, so a couple explorations that we did in class. It says first, let's graph sine x on this restriction here, right? And so we know sine x, the parent function starts at 0, 0, and then it's going to go up here, pi over 4, pi over 4 is like root 2, so it's root 2 over 2, so it's not quite 1. But we do know at pi over 2, it's at 1. Whoop, it's kind of weird. And then at negative pi over 2, if we plug that in, that's negative 1. Okay, we have intermediate points, but that's root 2 over 2, which, yeah, is not a really exact point for us. So we do our kind of curve like that. Looks something like that, a little hard to draw. And so a few of our ordered pairs are exactly what I just did right there to graph it. We have negative pi over 2 and negative 1. And then we also have 0, 0. And then our last one would be at positive pi over 2 and 1. Right? And so on our second graph here, it says here, let g of x be the inverse of that. So would g of x be a function? And so that would be yes. And if you remember, to figure out if an inverse of a function is a function, is we do the horizontal line test. So we'd say yes, it passes the horizontal. Remember, line test. Remember, vertical line test is to tell you if a function is a function. The horizontal is to tell you if its inverse is a function. So yes, if I draw a bunch of horizontal lines, it only hits the graph once. Okay, and so here, name a few ordered pairs. Remember, one of the things that you guys learned last year in Algebra 2 Honors is the fact that an inverse is just the flip of the original function. So we can just flip around these signs. Right, so all I did is switch the x and the y. The second one's easy peasy because 0, 0 switched is just 0, 0, pi over 2. Okay. And so those are some new coordinate points for our graph. Okay, and it says use the ordered pairs to sketch the graph g of x onto the same graph that we just did. In a couple things, it's a little harder to picture this. If we did pi over 4, I think that's something like 0.75, and then pi over 2 is about, I think it's 1.5. Okay, so just so we can get a feel for when I actually graph these ordered pairs for g of x. Okay. So the first ordered pair we'll do maybe in a different color for g of x. So we'll do that ordered pair. So negative 1. So it'd be not quite halfway in between, but somewhere in between negative pi over 4 and negative pi over 2. And then negative pi over 2 there. Again, that is like kind of 1.5-ish, right? So maybe somewhere in there. Next one's easy. Shabam, 0, 0. Next one's 1, so again, a little bit beyond the pi over 4, and then a little bit, kind of like right in the middle of the two there. Shabam. Okay, so that's going to be something that looks more like that. Okay, hard to draw, but that's the idea behind it. Okay, it says, what is the equation for g of x, that kind of stuff. The other way that we know that this is an inverse is, remember, if we draw that, oh geez, that is hard, y equals x line, it has to reflect over that guy. So that's another idea behind it. So it says, what is the equation of g of x? Well, g of x is just the inverse, right? And so it's a little bit different than the functions that we saw before, but the inverse of sine is literally just, we call it sine inverse. Okay, so that negative 1 is not necessarily like a power where we put it to the denominator, if you remember that. remember this one, x to the -1, we do 1 over x to the +1. We're not really thinking of that when we talk about inverses of our trig functions, okay? So that would be the inverse of sine. Nice. And then let's do another one here. It says solve the equation for all possible values of sine x equaling -1. So what we want to do is we're looking for the angle, right? So we're looking for the angle here. What angle gives me this? So if I go through a few of those x's, the first angle, if you think of sine, the first time I get a -1 is at 3 pi over 2. All right, so 3 pi over 2. And then if you, again, so down here. But then the next time I get it is I've got to go here. And then I got to go all the way around again. And so I'm going to add 2 pi to that. So my next one's actually going to be 7 pi over 2. And it keeps going, right? Our next one would be another full circle. So 11 pi over 2 and go on. So this is where we kind of call out where we have a pattern. So every 2 pi, it repeats itself, right? And so what we would say is we would say x is equal to the first one we come to, 3 pi over 2, plus 2 pi, that's our pattern, times the number of circles that we want to do, times n. And n could be positive or negative numbers, so we can spin in reverse. Okay. So then it says here, solve x over the restricted area of that. Okay, so notice that if you think about the restricted area, negative pi over 2 goes to here, and positive pi over 2 goes up here. Right? And so the restriction is kind of from here to here. So that's the restriction that we're dealing with right here. Right, so a little bit different. So here, if I solve it within this restriction, the point that I'm looking for is down here. So that would be at negative pi over 2. So negative pi over 2 is actually the same thing as positive 3 pi over 2. Same point, but just a different way to look at it. So it says here, why is the restricted domain useful? Well, it gives us only one answer, right? Whereas that first question, it just gives me, okay, well, when is it equal to -1? Well, with sine, cosine, all our trig functions, you have an infinite number of answers on those guys. Okay, so if I restrict the number of answers, it helps me give you one answer. Okay, so then it says here the restricted domain, this guy, is commonly used for finding angles for sine. Okay, why would this be? So the reason that we're looking at this is so if I draw, right, a sine function like that, right? So if I draw a sine function like that, this is what, 0, this is pi over 2, or sorry, no, that's pi, and this is 2 pi. This is pi over 2, and this is 3 pi over 2, right? So the reason I want to draw this restriction is because I want all the values for sine represented without me having to like jump. I want it to be continuous. So if you notice, if I I'll do maybe in a different color, let's do this nice blue. So if I look, these are all the positive signs of sine, right? So those are all the positive. Well, guess what? All of those values are repeated right there. So if I keep following along with my curve there, they just all get repeated. Well, the only thing I'm missing is I want all my negative signs here. Right, so all my negative values of sine. And then again, it gets repeated right there. So it kind of goes all the positives repeated, negatives repeated. Well, how can I make it so that it is continuous? I don't want to have this jump right there. I don't want to have to jump over values. So what I do is I take this value right here, here's all my positives up here, and then I take it down here, right? So this is negative pi over 2. So if you notice, if I work a little bit backwards, look, I get all of my positive and I get all of my negative values of sine. So every single possible answer for sine is represented in between this restriction right there. So from negative pi over 2 to pi over 2. So that's why we choose that restriction, is because it's continuous and it gives us the entire values possible for sine. Okay, and so this next page I've already filled it out for you because it's super duper repetitive, at least in this first column. So if you notice our sine inverses here, so sine inverse, I bring the regular sign to this other side, so sine of y is equal to x. It is not, like I started out the lesson, it is not where we take this negative value, this negative quote-unquote exponent, which it's not, and put it to the denominator. Okay, so we do not do this. This makes us very sad. Okay, so we don't do that. So if you notice here, and you can kind of pause it as we go through, but all of these show you that it's actually the cosine of y equals x and not 1 over the cosine of x. Okay, so I'll kind of scroll down. You can pause it and you can write down all of these values in this middle column. Okay, so go ahead, pause it, write all those down. But that's the idea, is that you bring the non-inverse trig function to the other side, and it's not brought to the denominator. Okay. All right. So now this is our restricted domain here. Okay. And so as you are thinking, as you're going through this, what you really want to focus on are the positive and negative values of whatever trig function we're talking about represented within this restriction, right? So for sine is your y values. So from here to here, so negative pi over 2 to pi over 2, all of your y values here are represented, okay, are shown within there. Whereas cosine, right, so maybe don't draw this part of it, but if I did the same restriction for cosine, right, do I get both the positive and the negative side of cosine? And the answer is no, right? If I drew it over here, I only get the positive cosines. Well, I want both of them, right? And so what I'm going to do for this is my restriction is going to be from 0 to pi, right? So I get all of my positives and I get all of my negatives represented there. It shows everything. It's continuous. So the default restriction for cosine is going to be 0 to pi. Okay, both of them included. Same idea for tangent, right? So tangent's very similar to sine. So everything is shown right here. This tangent's a little bit tricky, right? Because technically, never mind. I was going to say 0 to pi, but then the negatives down here. It's a little, yeah, tangent's a little bit tricky because if I go into the second quadrant, they do have those negative values of tangent there. Okay, so same idea, and then you can kind of follow the same restrictions. If you notice, very, very similar for everything else. Cotangent is different because that's the flip of tangent, so that's why it's 0 to pi. Here, this is the same idea as our buddy cosine, so that's the same. So it's the inverse, so it's the cosine. And then your cosecant, which is the same as, or inverses of sine down here at the bottom one. That's why it has the same restricted range on those. It'll take you some time to definitely think about it, but if you notice, your answer is pretty much either 0 to pi or negative pi over 2 to pi over 2. Okay, so that's pretty much your answers there. Okay, so here you'll see it's pretty rare for us to find the inverse functions of these guys. Okay, we don't typically do those ones. Okay, here's our range values. You can look, we got it from Earl the Great's website, mathguy.us. It says here, you can kind of look at where these inverses, where we will find them, okay? And so these are all, again, you'll see the principal solutions, you'll see that term. That's kind of, principal solution means the solution within that given range there, okay? So this is where it's at. So sine inverse is here, cosine inverse is quadrant 1 and 2. Tangent's going to be 1 and 4. Okay. So that's the tricky part. Okay. So it says find the exact value of each inverse trig expression. Use the restricted range to find the principal solution. Okay. So no calculators on this one. And then rationalize if we need to. Okay? So what we're going to do is we're going to think of, so sine, if you think of our restrictions, sine is from negative pi over 2 to pi over 2. So it's going to be somewhere within there. Okay. Since sine is positive in the first quadrant. So it needs to be somewhere up here. And so if you think of what value is going to make sine, what angle, I should say, what angle is making sine root 3 over 2? We look at our angle root 3 over, pi over root 3, which if we look at the coordinates is 1/2 root 3 over 2. And this is what we're looking for right there, that guy. Okay, so we're looking for the angle, because remember, whenever we do the sine inverse, we're looking for the angle of that gives us that value. So the angle that would give us that value is pi over 3. Now again, there's an infinite number of answers that would give us sine of a sine value of root 3 over 2, but we're looking for within the restricted range. Okay. Now cosine is from 0 to pi, so somewhere in here. Now where would cosine give me root 3 over 2? Okay, which angle? And so that would be pi over 6, which gives me root 3 over 2, comma 1/2. Again, I'm looking for that value right there. So my answer is going to be pi over 6. That's the angle that gives me that value. I could easily change it and say, okay, well, how about negative root 3 over 2? Well, then my answer would be over on this side. Okay. Now cosine, same thing. 0 to pi. That's my restricted range. Now we do have a negative, so I know cosine's negative over here. So this one is going to give me pi over the reference angle would give me pi over 3, but this one is 2 pi over 3 since it's in the second quadrant there. Again, the values of this would give me negative 1/2 root 3 over 2. We're looking for that idea right there since it's cosine. So my answer is 2 pi over 3. That's the angle I'm looking for. Now tangent, right? So tangent is going to be in those two quadrants. Tangent's positive over here. And of 1, thankfully, this is going to give me pi over 4 because remember root 2 over 2, tangent is sine over cosine. So we do that. This one divided by this one, which they're the same, so that would give me 1. So pi over 4 would be my answer. That would be my answer within the restricted area. Okay. Now the next one's a little bit tricky, right? So here's my restricted area. So negative pi over 2 to pi over 2. It's negative, so I know it's got to be down here in the fourth quadrant. All right, so it's got to be in the fourth quadrant. But I know that my coordinates are going to either be 1/2 negative root 3 over 2 or root 3 over 2 1/2 negative 1/2. Right? And so which one of these is going to give me an overall value when I divide it of root 3 and this right there. So if I do negative root 3 over 2 divided by 1/2, I'll get root 3. Okay, so in that case, what we want is we want this angle that's, oh, geez, more down here. Well, that's terrible. Hard to draw on this guy. So somewhere down there. And so that right there, that would give me negative pi over 3. Kind of like 60 degrees, but going down, right? So going clockwise instead of counterclockwise like we like it. So that would be negative pi over 3. That's where we would find that answer. Cool. And our last one here is cosecant, right? So cosecant, if you think about that, cosecant's the inverse of sine. And when we have that, whenever I take the inverse, I just flip it. So it's going to be negative 2 over 1. So for sine is going to be negative 1 over 2, right? So sine negative 1 over 2. So for sine, I go right here. So I would have, for this one, I'm going to have this value of negative pi over 6, which again gives me the x, but all I really care about is the y value, since I'm looking at sine in this case. So sine, since that's negative 1 over 2, cosecant, it would be negative 2 here. Okay, so that's the answer I'm looking for, pi over 6. Okay, so not a whole lot of work or math behind it, but definitely a lot of thinking behind there. Okay, so now here, find the exact values. Some of these are pretty straightforward, but some of them get a little bit challenging. Okay, so again, just kind of thinkers. So here within the restricted range provided. Okay, and so for cosine, that's a restricted range. And so whenever you have sine or cosine, cosine inverse, sine, sine inverse, they typically just cancel each other out. The trick is you need to make sure that this still falls within the range, right? So if I put this in decimal form, this would be 0 to 3.14-ish, right? Pi. So is that within our restricted range? And the answer is yes. So we're good with that. Now, the tricky part is that, say, if the answer was like 3.7, that would cause us some problems and we'd have to do something, which we'll get to later. Okay, so same thing, sine here. So sine, shabam right there. Okay, so those guys cross out, and our restrictions from here to here. Can I have a negative 1 within here? And the answer is yes. This is negative 1 down here. So those just cancel and leave me with negative 1. Notice the difference between these upper examples that only gave you one trig function, whereas these second ones give me 2. So I kind of work on the inside and then work out, especially like on number 9. Okay, so tangent. So tangent, we're going to work on this part of it first. So tangent gives me the restricted area right in here. So positive gives me an angle like this, right? So make up my own triangle. I'm going to delete the restriction just so I can see my triangle a little bit better. Okay, and so tangent is opposite. Here is our angle. So opposite over adjacent. This one's nice because it's a 3, 4, 5 triangle. And so now what I do, once I set it up, I kind of ignore this. And now I solve for sine, right? So sine of this angle would now be 3 opposite over hypotenuse. So 3/5. Cool. Now cosine, and again, cosine, our restriction is right in here. Now cosine's negative, so it's going to be in the second quadrant. Notice how I'm always going to make that right angle with the x-axis. So I'm going to go through and delete my restrictions again, hopefully. There we go. Just so I can see the picture a little bit better. Now cosine is adjacent and hypotenuse. Be careful with the sine. You have to determine which one of these should be negative, and it's always going to be this one on the negative x-axis. Okay, so then once I've done that, then that's gone. And I solve this out right here. I get 7 squared is equal to 6 squared plus We'll call it y squared. And so what's that? Y squared is equal to 49 minus 36. So y is equal to the square root of 13. Okay, so the y value here is square root of 13. Now tangent's going to be opposite over adjacent. So root 13 over negative 6. I'm going to bring that negative out in front and call it a day. I don't need to rationalize it because the root's in the numerator. Nice. Okay. Number 11, this is kind of part of the thing I was talking about earlier, but if I cancel these, my answer should be 2, right? But the tricky part is 2, can I get 2 when I'm dealing with just a regular sine function? And the answer is no. 2 is outside of our maximum value. So the max value of sine that I can get is sine of any angle there is 1. So therefore 2 is just too big. So x cannot equal 2. Okay. Again, the reason being, think of a sine function. I go like this. My max is 1. My min is negative 1. So it's just outside of there. Nice. Okay. We got just a couple more examples here. Now we're just going to use some algebraic expressions, but it's the same idea. So we kind of work on the inside first. So sine is going to be in that first and fourth quadrant. So in these two, I won't draw the thing so I don't have to erase it. Now sine is positive, so that tells me it's got to be up here. And now this is where I always see students get tricked up. Remember, you can always put this over 1, right? So sine of an angle is going to be opposite over adjacent. Or sorry, opposite over hypotenuse. Right? So opposite over hypotenuse. And so what I need to find is I need to find this last value down here at the bottom. And so that's going to be 1 squared is equal to x squared plus, even though there's an x there, we'll call it b squared. All right, so I want to know what b is equal to over here. So b squared is going to equal 1 minus x squared, square root it. So b is going to equal square root of 1 minus x squared. Nice. And so then what I'm looking for is cosine. So cosine is going to be adjacent, so 1 over x squared divided by hypotenuse, which is 1. So we can simplify that. We don't need the 1 in the denominator. So 1 minus x squared. Ta-da! Nice. Okay, and so this one here says, given that x is greater than 0, aka on the right-hand side, right, so positive. Tangent, again, tangent is positive in the first, so tangent is opposite over adjacent. So this value up here, my c value, is going to equal c squared is equal to 1 squared plus x squared. So c squared is going to be the square root of 1 plus x squared. Cool. And so now if I look at secant, remember secant is inverses with cosine. So cosine is adjacent over hypotenuse. So secant is going to be hypotenuse over adjacent. So this one would be 1 plus x squared over adjacent. That looks like an h, but it's a 1. So my final answer is 1 plus x squared. Nice. Well, there you go. I hope you enjoyed it. That's 4-7. One more section to go, and you are all done.